Okay, for what we have, moving on um, from the eigenvalues and eigenvectors, we have moving on into the next chapter. Okay, we have what will be referred to as inner product length and orthogonality. And much of this stuff is going to be carried over from um, what we have had at the end of Math 172, okay, where we had dealing with vectors, dot products, magnitudes, all that good stuff. And we have, in the case of what we have for the first item, now the author refers to inner product, and this is what is also referred to as dot product. And for those who will be taking Calculus 3, you will be looking at dot products among other items like cross products and magnitude. And now we have for two given vectors, okay, we have u and v. And for the inner product of u and v, or the dot product of u and v, okay, that is going to be equal to the transverse of u times v. And just as a case here, say if we have three given vectors, u, v, and w, we have u to consist of 1, 2, 3, and we have the vector v to consist of the elements negative 1, 0, 5, and w equal to the vector where we have the elements 3, negative 4, and 2. And we have determining the following. Say if we are looking at the dot product of u and v. Okay, so looking at taking the transverse of u and multiplying by v. Again, you have transverse of u. Okay, we have just in the row arrangement, we have 1, 2, 3. And you have times v, you have negative 1, 0, 5. And multiplying, you have negative 1 times 1, 0 times 2, 5 times 3. And combined, we had the inner product of u and v to end up at 14. And say that in working with the same vectors, say we have taken the dot product of v and w. And this time we take the transverse of v multiplied by w. And so multiplying together, have 3 mapped with negative 1, negative 4 with 0, negative 2 with 5, and multiplying and combining what we have in this particular case. All right, we have the result to end up at minus 13. Now, let's say that if we're looking at taking the sum of vectors, and we're taking the dot product between the resulting sum of u and w, and we have with respect to v. Now for u plus w, if I were to take the sum of these two vectors, okay, we have the result to be at 4, negative 2, and 1. And taking the dot product between that sum and v, okay, so you have 4, negative 2, 1, and you have from v, again, we have negative 1, 0, 5. And with the sum out at the front, I'm going to be taking the transverse of this. So putting the 4, negative 2, and 1 in row formation, multiplying by, or taking the dot product with v at negative 1, 0, 5. So I have negative 1 mapped with 4, 0 with negative 2, and 5 with 1. And so we're going to end up with negative 4 plus 0 plus 5, and the outcome we end up as 1. All right, now other terms, okay, and now for the length of a vector v, okay, this is also referred to as the magnitude of v, where we have v to consist of among the elements like x of 1, x of 2, and we can have x of n designated as the bottommost or the last element, and this will be defined by, and the notation, again, you have, well, it looks like a double absolute value sign, but this will be in reference to the length or the magnitude of v, and this will be equal to, in one context, the square root of the dot product between v and itself. And in terms of notation, okay, we also had the square root of x of 1 squared plus x of 2 squared all the way out to the last element squared. And just in the case of looking at what we have coupled with the length of a vector, we also have what is referred to as a unit vector. And a unit vector, by definition, is going to be a vector whose length is going to be at 1. And okay, and we have for a given vector v, a unit vector heading in the same direction as v is going to be where we have, say we have the unit vector u is going to be equal to the vector v divided by its length or magnitude. And just little sample here. Okay, say we have a 4x1 vector v. Okay, and just our notations here, we have v is equal to 1, 2, 3, 4. Again, this is just the notation going back to the first chapter, but the more common, again, we have with the 1, 2, 3, 4 in column formation and bracketed. Okay, it says to determine the magnitude of v as well as the unit vector heading in the same direction as v. So looking at what we have here, now for the magnitude of v, again, this will be taking the square root, the sum of the squares of 1, 2, 3, and 4, and the outcome in this case, it will be the square root of 30. And as for a unit vector heading in the same direction as v, okay, so we have v divided by the magnitude. Again, we have v at 1, 2, 3, 4 divided by the square root of 30. And the outcome, we have 1 over the square root of 30, 2 over the square root of 30, 3 divided by the square root of 30, and 4 over the square root of 30. All right, and we have sort of tying in together what we have for length. Okay, we have distance between vectors. Okay, and so you have two vectors, u and v. We have the distance between these will be equal to the magnitude of the difference between the vectors u and v. And let's say that if we have a couple of 3x1 vectors u and v, and we're looking at the distance between them, so we have u to consist of 9, 6, 3, and v to consist of -1, -2, and 7. All right, so we have for the difference between the vectors, so we have subtracting the corresponding elements. We have 9 minus -1, 6 minus -2, 3 minus 7. So the difference vector comes out to 10, 8, and -4. And in terms of the distance, okay, again, we're going to be taking the square root of the sum of the squares of 10, 8, and -4. And so we had the square root of 180, and this is a radical that can be reduced. Okay, 180 is not a perfect square number, but it is the multiple of a perfect square, the highest being 36. Square root of 36 is 6, and we have the factor of 5 left over. So in exact reduced radical terms, the distance between the vectors u and v will be 6 times the square root of 5. Now a term that you'll be hearing time and again if you take Calculus 3 will be orthogonality. And what that means is that you're looking at perpendicular formation. Now, for two vectors, u and v, they will be said to be orthogonal or geometrically perpendicular to each other if, in one capacity, the dot product is equal to 0. Also, if the vectors are orthogonal to each other, you will have that the magnitude of the sum of the vectors will be equal to the sum of the squares of the magnitudes of each vector. Okay, so you have the sum of the vectors squared, okay, will be equal to the sum of the squares of the magnitudes of u and v. And just quick sampling. And say we have a couple of 4x1 vectors with u and v. And it says here to show that these will be an orthogonal pair. So in the first case, if we look at it from the vantage point of the dot product being equal to 0. So again, we have with u and v. Okay, again, the dot product between u and v will be taking the product between the transverse of u and v. Okay, so for the transverse of u, we have in the row formation, we have 3, 4, -2, 5. Again, we have v in column formation with -4, 6, 11, 2 as we run down. And so mapping together, we have -4 times 3, 6 times 4, 11 times -2, and 2 times 5. And so we have -12 plus 24 is 12. Take away 22, so you have -10. And we have plus 10 is equal to 0. So we have the dot product to be at 0. So this is one bit of evidence to show that these are orthogonal vectors. But also, if we have just taking the Pythagorean equation. Now, for the magnitude of u, okay, taking the sum of the squares of the the elements. Okay, so you have 3 squared, 4 squared, negative 2 squared plus 5 squared. Squaring these, this will come out to the square root of 54. And as for v, taking the squares of the elements and adding together, okay, we had the square root of 177. And for the sum of the vectors, okay, we have negative 1, 10, 9, and 7. And for the magnitude, okay, so we're looking at taking the sum of the squares of negative 1, 10, 9, and 7, and taking the square root of the sum. So we had the square root of 231. So again, just for this feature, okay, so taking the square of the sum of the vectors, okay, so we had the square root of 231 squared. Magnitude of u, we had the square root of 54. This will be squared. That of v, we had the square root of 177 also squared. So we have 231, okay, on the left-hand side. To the right, I have 54 plus 177. And taking the sum on the right, we had 231 is equal to itself. And so u and v, from that vantage point, also proven to be, once again, orthogonal to each other.